In this section, we're going to look at the rotation of a rigid object about a fixed axis. Rotation of a rigid object about a fixed axis. So let's say this is the rigid object, and let's say this one is rotating about this axis. Okay, so each particle is rotating about this axis in a circular path, right? Something like this. All right, each particle will be rotating about this axis, each particle of this whole object. So in this section we're going to deal with angles because we're talking about rotation about a fixed axis. So I'm going to start by defining units of angles. There are two units of angles in common use. One of them is a degree, which we use in our daily purposes, and the other one is radian, which is used for scientific purposes. So let's look at units of angles. First of all, an angle is a measure of the inclination between two lines. Okay, so there are two units in common use. There are two units in common use. They are the degree and the radian. The radian is the unit we use for our daily purposes, and the degree is the unit we use for our daily purposes, and the radian is the unit used for scientific purposes. So let's start by defining a degree. A degree is defined to be 160th of a complete revolution of a complete revolution. Okay, so a complete revolution is this one over here, complete circle. So what we call a degree is 1/360th of this complete circle. What that means is this angle over here is 90 degrees. Okay, so we can say that one revolution equals 360 degrees. Okay, so this means one revolution is equal to 360 degrees. Okay, so that's how a degree is defined. It's 1/360th of a complete revolution, which means one revolution is equal to 360 degrees. All right, and then we have the radian is the scientific unit. This one is defined in terms of a central angle, which means an angle formed at the center of a circle. One radian is defined to be a central angle, the subtendus, and arc length is equal to the radius. Okay, this is a radian, or let's say one radian is defined to be a central angle that subtendus or opens an arc length equal to the radius. Okay, so let's see what we mean by this. Suppose we have the following circle. Let's say the center is over here. This is the radius. So the angle that subtendus and arc length is equal to the radius. Let's see something like this. Okay, if the radius equals this arc length over here, then the measure of this is defined to be 1 radian. Okay, so it is a central angle that subtendus and arc length is equal to the radius is 1 radian. So this is the radius. Let's say this is the arc length equals r, then this one over here is 1 radian. Okay, now suppose we have an arbitrary central angle like this. Let's say we have this one, the radius, so this is an arbitrary angle, not necessarily equal to 1. Okay, so generally the radian measure of this angle is defined to be the ratio between the arc length and the radius. Okay, so the central, let's say the radian measure, the radian measure of a central angle, according to this definition of a central angle, is equal to the ratio between the arc lengths subtended by the angle, or opened by the angle, and the radius by the angle and the radius. Okay, so if this is an angle in radians, theta, then theta equals S divided by R. Okay, all right, so an angle measured in radians is equal to the arc length subtended by the angle divided by the radius. Now let's find out the radian measure of one revolution. Okay, so if theta equals 1 revolution, then what is the arc length subtended by 1 revolution? Obviously, if theta is 1 revolution, the arc length subtended by 1 revolution is the circumference. So if theta is 1 revolution, then S equals circumference of the circle, which is 2 pi r. So it follows that 1 revolution in radians is circumference divided by the radius. In other words, one revolution is equal to 2 pi radians. Okay, so 1 revolution is equal to 2 pi radians. That is, let's say this is complete revolution, therefore this angle over here is 1/4 of 2 pi, or pi over 2, that is pi over 2 is equivalent to 90 degrees. Okay, now let's look at the relationship between a radian and a degree. Okay, relationship between a radian and a degree. Okay, now we know the value of 1 revolution in both degrees and radians, right? So we can say 1 revolution is equal to 360 degrees, but also is equal to 2 pi radians. Okay, so from this it follows that a degree is equal to 2 pi divided by 360 radians, or simplified. So a degree is equal to pi over 180 radians. Okay, so this is the relationship between a degree and a radian. Or you can cross multiply and express radian in terms of degrees, and also you can say a radian is equal to 180 over pi times a degree. radian equals 180 over pi degrees. Okay. Okay, now let's look at some conversion examples. Let's say convert maybe 60 degrees to radians. Okay, we're going to convert 60 degrees to radians. All right, now 60 degree, now I can replace degree by this one, right? So that equals 60, but 1 degree equals pi over 180 radians, right? So that follows, this is pi over 3 radians. Okay, so we can use this relationship to convert between degree to radian or radian to degrees. B, let's say convert pi over 4 radians to degrees. Okay, so we have pi over 4 radian equals pi over 4. Now, what does radian equal in terms of degrees? We got right here. A radian is 180 over pi degree. This is 180 over pi degree. And we get pi goes with pi. 180 divided by 4 is 45 degrees. Okay, so this is 45 degrees. All right. So probably in most problems you'll be given the angle in degrees, but the unit used for scientific purposes is radians. That is, in mathematical equations you have to use radians. So you have to convert the degrees to radians before you can use the mathematical equations. And another note I want to make is a radian is unitless. A radian is unitless because it is length divided by length. Okay, you see, this is arc length divided by the radius. Both are measured in meters. That's why it is unitless. Okay, now before we deal with the dynamics of angular motion, we're going to define the motion variables for angular motion or rotational motion. Okay, so motion variables of an angular motion. Okay, so in this case what we have is we have particles rotating in a circular path of constant radius. Only the angle changes, so we have to deal only with the angular position because the radius is a constant. Okay, so the first physical quantity is angular position. Angular position. We're going to use theta to represent this one. Okay, and since obviously is radians. So basically we're talking about circular motion over here. If you've got a rigid body over here, and let's say it's rotating about this fixed axis, a particle over here is actually revolving in a circular path. Okay, so each particle in the solid is revolving in a circular path. So basically we're talking about a circular motion over here. Okay, so let's just look at a circular motion for a given particle. Okay, suppose let's say we have, this is the trajectory of a particle, of any particle in this solid object. Okay, so what we call angular position is the angle between the positive x-axis and the position vector of the particle. Let's say the particle is over here. This is the position vector of the particle. This is the angle that we call angular position. Okay, so this is angle formed between the position vector of the particle position vector of the particle and the positive x-axis, the positive x-axis. Okay, and remember, angles in a counterclockwise direction are taken to be negative, and angles in a clockwise direction are taken to be negative, and obviously the unit is radian. Okay, and then the next physical quantity we need to define is angular displacement. Angular displacement. We're going to use delta theta to represent it. This is basically change in angular position. This is change in angular position. Okay, it's simply delta theta equals the final position of the final position vector minus the position of the initial position vector. Okay, so let's say a particle is revolving in this circular path over here. Let's say its position changes from here, where this one is theta I, to this, where this angle is theta f. This is theta f, so this is delta theta, the difference between the two. This is delta theta equals theta f minus theta I. Okay, we got theta I, theta f, and the difference is the angular displacement. Okay, and then we're going to look at average angular velocity. Average angular velocity. This is defined to be angular displacement per a unit time. This is defined to be angular displacement per a unit time, per a unit time. So we're going to use omega bar over here. Omega, the bar stands for average. So the definition of this one mathematically is delta theta divided by delta t. Okay, or you can say theta final minus theta initial divided by t final minus t initial. You can usually assume the initial time to be 0, so it will be theta final minus theta initial divided by the time taken. Okay, so this is the definition of angular velocity. All right, the unit, as you can see from here, the unit of angle is radian, so the unit is radian per second. All right, radian per second. And then we have instantaneous angular velocity. Instantaneous angular velocity. You can say this is angular velocity at a given instant of time. Okay, but we can also say it is average angular velocity evaluated at a very, very small interval of time. Okay, so let's use that definition. This is average angular velocity evaluated at infinitesimally small interval of time. Small interval of time. Okay, there is a way of writing this in calculus, as you know. So you start with the definition of the average velocity, delta theta by delta t, and then you take the limit of this expression as delta t approaches 0. That's what we call the instantaneous angular velocity. But as you know from calculus, this is the definition of the derivative of angular position with respect to time. Okay, so angular velocity is equal to the derivative of angular position with respect to time. All right, And then we have average angular acceleration. Average angular acceleration. Okay, we're going to use alpha for this one. Average angular acceleration. So this is change in angular velocity per a unit time. This is defined to be change in angular velocity per a unit time. Per a unit time. So mathematically, there's a bar over here. This is average. Alpha bar is delta omega, or change in angular velocity, divided by the time taken for this change. Okay, or we can say this is omega final minus omega initial divided by t final minus t initial, but you can usually assume the initial time to be 0. So you've got omega final, omega initial divided by time. Okay, so this is the definition of average angular acceleration. Okay, now let's look at the unit of alpha. This is obviously the unit of angular velocity, which is radian per second, divided by the unit of time, which is second. So the unit of angular acceleration is radian per second square. Okay, and then finally we have instantaneous angular acceleration. Instantaneous angular acceleration. This is angular acceleration at a given instant of time. Okay, but we can also say this is average angular acceleration evaluated at a very, very small interval of time. So this can be defined to be average angular acceleration evaluated at a very, very small interval of time. So let's write this mathematically using calculus. So you start with the definition of average angular acceleration, which is delta omega by delta t, and then you take the limit of this expression as delta t approaches 0, and that is a derivative of angular velocity with respect to time. That's what you call instantaneous angular acceleration. So alpha is the derivative of angular velocity with respect to time. All right, so these are the motion variables we need to discuss angular motion. Now, before we proceed, let's look at the relationship between angular and linear variables. Relationship between linear and angular variables. Okay, well, these are the linear variables. For displacement, we have delta x, and the corresponding angular variable is delta theta. For speed, we have v for linear speed. For angular speed, we have omega, and for linear acceleration, we have a, and for angular acceleration, we have alpha. Okay, so we want to find the relationship between these variables. So we're going to start with the definition of radian, or angular position. As you remember, an angle measured in radians is defined as the arc length divided by the radius, right? So you've got this angle, this is r, and this is s. Then this angle theta is defined to be the arc length divided by r. Now this is linear distance, okay? This is a distance over here. So this is the linear variable, and this is the angular variable. And remember, the radius is a constant right here because it's moving in a circular path, okay? So from this, we have S equals radius times theta. Now let's take the change of both sides. So delta S, that's linear displacement. R is a constant, so it's going to be R times angular displacement, okay? So this linear displacement is equal to radius times angular displacement. So this is the relationship between linear displacement or arc length and angular displacement, okay? Now for a circular path, we can write as delta S instead of delta X as arc length, okay? All right. Now to find the relationship between linear velocity and angular velocity, we'll simply divide this equation by delta t. So you've got delta S by delta t equals radius delta times delta theta by delta t. But if you remember, this is velocity, distance divided by time is velocity, and this is angular velocity, omega, right? So we have this relationship, linear velocity equals the radius of the circular trajectory times the angular velocity, okay? And then to find a relationship between tangential acceleration and angular acceleration, we take the change of both sides. So delta v, again radius is a constant, so you can take it times delta omega, right? So you see this is change in velocity in tangential speed per unit time, and this change in angular velocity per a unit time, okay? Now remember, this is tangential acceleration, that is the acceleration due to change of speed, okay? And this radius times this one is angular acceleration, okay? So if you've noticed the pattern, to convert an angular variable to a linear variable, all you have to do is multiply by the radius, okay? You get angular displacement, you multiply by the radius, it becomes linear displacement. You've got angular velocity, if you multiply by the radius of the circle, it becomes linear velocity. You get angular acceleration, if you multiply it by the radius, equals tangential acceleration, okay? Now we're going to specialize to a special kind of motion as we did before, and that is uniformly accelerated angular motion. So we're going to look at uniformly accelerated angular motion, that is motion in a circular path, okay? So what does this mean? This is motion with constant angular acceleration, or motion where the angular velocity is increasing at a constant rate. So this is motion with a constant angular, or you can say tangential angular acceleration, okay? So that is a motion where alpha is a constant, okay? So for this kind of motion, alpha, or the angular acceleration, is constant, okay? So what does alpha equal to? Alpha is the derivative of angular velocity with respect to time, right? So we can say d omega equals alpha dt. Now remember, for this kind of motion, alpha is a constant. Now let's integrate both sides. As the time varies from 0 to t, this varies from initial angular velocity to a final angular velocity, okay? So this side gives you omega final minus omega initial equals, remember alpha is a constant, so this just gives you alpha t. So we get the first equation, omega final equals omega initial plus alpha t. Okay, so this is one of the equations you can use for this kind of motion. We have dealt with this for the case of linear motion, so we're going to get identical variables, identical formulas with angular variables. Okay, now we have angular velocity is equal to the derivative of angular position with respect to time. Okay, so if we replace that by this one, we can say d theta by dt equals initial angular velocity plus angular acceleration times time, right? And then we have d theta equals omega I dt plus alpha t dt. Okay, so as this changes from initial angular displacement to final angular displacement, this changes from 0 to t. Okay, from 0 to t. So this side gives us theta final minus theta initial, which is delta theta. Okay, this is delta theta. That equals, this is omega I times t, and this gives us 1/2 alpha t squared. Okay, so the second formula we can use is delta theta equals omega it plus 1/2 alpha t squared. Okay, now these are the only two independent equations we have, but we can add a couple of other equations so it'll be easier to solve problems. Okay, let's start with the definition of average angular velocity, that is delta theta divided by time. Okay, so we get omega it plus 1/2 alpha t squared divided by t. Okay, so what do we get? We have average angular velocity equals omega I plus 1/2 alpha t. Okay, but what does this equal to? You see, the first equation we have obtained, this one over here, alpha times t equals omega f minus omega I. Okay, so we can say that but alpha t equals omega final minus omega initial. So we have the following: average angular velocity equals omega I plus 1/2 omega final minus omega I. Okay, so we can combine this with a common denominator 2, so we've got 2 omega I plus omega final minus omega I, and we get the average angular velocity is the sum of the initial angular velocity and the final angular velocity divided by 2. So for this kind of motion, for uniformly accelerated motion, the average acceleration is simply the average of the initial and final angular velocity. It might look like this is true for any kind of motion, but it's true only for a uniformly accelerated motion. Okay, now using this, let's get formulas for delta theta. You see, delta theta is average angular velocity times time. You see over here, times time. And then we replace this for average angular velocity. We get omega I plus omega f over 2 times t. Okay, so we have another equation over here. Delta theta equals omega initial, omega final over 2 times t. Okay, so we can put that in a box. That's the third equation we can use. But remember, only the first equations are independent. This equation and this equation are dependent. These are dependent equations, which means they're obtained by combining these equations. All right, now let's substitute for t. Okay, so we've got the following formula: omega final equals omega initial plus alpha times t. That tells us t equals omega final minus omega initial divided by angular acceleration. Okay, so let's start with this formula. Delta theta equals omega I plus omega final over 2 times t. So that is omega I plus omega final over 2 times this expression over here, omega final minus omega initial divided by alpha. Okay, so this is the product of sum and difference. If you remember algebra, is simply equal to the difference between the squares. Okay, so you've got delta theta equals omega final squared minus omega initial squared divided by 2 alpha. Okay, this is customarily written as the square of the final angular velocity equals the square of the initial angular velocity plus twice alpha times delta theta. Okay, so these are the equations you can use if you know the motion is a uniformly accelerated motion. Okay, so let's put these formulas together. Equations of a uniformly accelerated angular motion, or motion in a circular path. Okay, so the first one was omega final equals omega initial plus alpha t, and then you've got delta theta equals omega it plus half alpha t squared, and then you've got omega final squared equals omega initial squared plus 2 times angular acceleration times delta theta, and then we have delta theta equals omega initial plus omega final over 2 times time. Okay, so these are the equations you can use for a uniformly accelerated equation. Now you see in these equations there are 5 variables. We've got omega f, omega it, alpha, and delta theta. But as I've said before, only 2 of these equations are independent, which means you can solve only for 2 variables. So if you know any of these 5 variables, then you can usually solve for the other 2 variables. Okay? Now there are 5 variables. There are 5 variables in this equations. That is omega final, omega initial, t, alpha, and delta, and 2 independent equations. So that means you can solve only for 2 variables. So the conclusion is, if you know any 3, you can solve for the other 2. Okay, all right. Let's look at an example. Let's say we have this solid object over here. Okay, it's rotating like this. All right. Let's say the angular speed, or the angular velocity, of the rigid object shown, let's say, increased from, let's say, 5 radian per second to 15 radian per second, let's say in 5 seconds. Okay, and let's say we have let's look at this particle. Let's say this particle is at a distance of 2 centimeters from the axis of rotation. Okay, let's call this P. Let's say particle P particle P is at a perpendicular distance of 2 centimeters, let's say, from the axis of rotation. Now you see the angular variables are shared by all the particles of the solid. All the particles move with the same angular speed and with the same angular acceleration. So the angular variables are shared by all the particles of this solid. They all have the same angular speed, they're rotating together. They all have the same angular acceleration because they're rotating together, and they have the same angular displacement because they're rotating together. Okay, but if you talk about linear displacement, you see this part, if you compare this part and this particle is moving in a circle of smaller radius, this particle is moving in a circle of a bigger radius, so as a result they'll have different linear speeds. All right, now let's ask some questions. A, calculate the angular acceleration of the rigid body. Acceleration of the rigid object rotating about a fixed axis of the rigid object. Okay, so we want to find alpha. Okay, but we know alpha equals omega final minus omega initial divided by t, and we're told omega initial is 5, omega final is 15, and time is 5. Okay, so the angular acceleration for this solid, is 15 minus 5 divided by 5. Okay, so that is 10 divided by 5 is 2 radian per second square. All right, now let's calculate the tangential acceleration of particle P. You see particle P is moving as this object rotates in a circular path. Particle P is moving in a radius of 2 centimeters. Okay, in a circular path of radius 2 centimeters. So B, let's say, calculate the tangential acceleration, of particle P. Okay, so tangential acceleration is related with angular acceleration by radius of the circular trajectory times angular acceleration. Okay, the radius is 2 centimeters or 0.02 meters. The angular acceleration we just calculated is 2 radian per second square. Okay, so the tangential acceleration is the radius times the angular acceleration, radian per second square, and that is 0.04 meter per second square. Okay, C, let's say calculate the angular displacement of the rigid body. Calculate the angular displacement of the rigid body. Okay, that's basically the angle by which it was rotated. Okay, the rigid object. Okay, so we're looking for delta theta. Okay, that's what we're looking for. Now we just have to pick one of those equations. I think we can use this equation. Delta theta equals omega it plus half alpha t squared. Okay, the initial angular velocity is 5, the time taken is 5 plus half, the angular acceleration is 2, and the time is 5 squared. Okay, So we have 25 plus 25, that is 50 radians. Okay, so this object was displaced by 50 radians. All right, now that is CD, calculate the distance traveled by particle P, okay? Now we're looking for the arc length traveled, or delta S, okay? That's what we have to find. But we can express delta S in terms of the angular displacement, which is radius times angular displacement, okay? So the radius is 0.02. We just calculate delta theta to be 50, okay? So this one is 10 times 100 divided, I think it's just 1. So this is 1 meters, all right? So the distance traveled by the particle is 1 meters, all right? Now we're going to define an important quantity in rotational motion. It's called moment of inertia. Let's define moment of inertia. Okay, now you see, we've seen that angular velocity corresponds to linear velocity, angular acceleration corresponds to linear acceleration, angular displacement corresponds to linear displacement. Now the question is, what is the value that corresponds to mass in rotational motion? So this is a quantity that is similar to mass in rotational motion. So you can say that moment of inertia is to rotational motion as mass is to linear motion. So this is the physical quantity that serves the same purpose as mass for linear motion. Okay, so let's define it. Suppose, let's say we have this object rotating in a circular path, while rotating about a fixed axis. Now if we take this particle over here, let's say its mass is m, and then the perpendicular distance between the axis and the particle is r perpendicular, this moment of inertia I is defined to be mass times r perpendicular distance, okay? This is the definition of moment of inertia. So we can say that moment of inertia is defined to be the product, let's say this moment of inertia as I of a particle rotating about a fixed axis is defined to be the product of its mass and its perpendicular distance from the axis of rotation. Its perpendicular distance from the axis of rotation, okay? From the axis of rotation. That's the definition of moment of inertia. The mass times the perpendicular distance between the axis of rotation and the particle is what we call the moment of inertia. So you see, this quantity depends on the axis of rotation. Depending on the axis of rotation, this value could be different, okay? So this is a quantity that depends on the axis of rotation, or on the distance from the axis of rotation. All right, now let's look at the unit. Well, it's obviously the unit of mass, kilogram, times the unit of distance squared, okay? So the unit of moment of inertia is kilogram times meter squared. All right, how about if you've got a number of particles? Let's say these particles are connected by massless rods over here, okay, like this. They're connected by massless rods and they're rotating by this axis, okay? How do you calculate the total moment of inertia? All it is, you calculate the moment of inertia of each particle. That is, you take its distance from the axis, you multiply by the mass. You do that for every particle, and you add them. That's the total moment of inertia. If there are a number of particles, if there are a number of particles, the moment of inertia of the particles is simply the sum of the moment of inertias of the particles, of the moment of inertia of the particle, of the particles, okay? So if you've got particles m1, m2, m3, and so on at perpendicular distances, r perpendicular 1, r perpendicular 2, and so on, then the moment of inertia is m1 r perpendicular 1 squared plus m2 r perpendicular 2 squared, m3 r perpendicular 3 squared, and so on. Or we can write in terms of summation. This is the summation of over I, mi, I perpendicular I squared, okay? So if you've got a number of particles, all it is, you calculate the moment of inertia of each particle and you add them together, okay? Now let's look at rotational kinetic energy. Rotational kinetic energy. Now the formulas for linear motion and rotational motion are symmetric. All you have to do is replace the variables of the formulas for linear motion with the corresponding rotational variables, okay? So we know that the formula for linear kinetic energy is half m speed squared, okay? So this is for linear. Now if you want to find the formula for rotational kinetic energy, we've seen that mass is to linear motion as moment of inertia is to rotational motion, linear speed is to linear motion as angular speed is to rotational motion. So this is going to be the formula for rotational kinetic energy, but we can derive it this way. Let's say we have this particle revolving around a circular path, let's say with a linear speed v, and let's say its mass is m, okay? Its linear kinetic energy Now we can look at this motion in three different ways. Either we can look at it as a linear motion in this circular path, or we can look at it as rotational motion about the axis of rotation. Okay, so if you look at it as a linear motion, the formula is half times mass times speed squared. Okay, now suppose the radiuses are perpendicular. We know that this linear speed is the radius times angular speed. Okay, so if we put m and then v are perpendicular times omega, we get the following formula: half m r perpendicular squared, this is square over here, times omega squared. But remember this is moment of inertia, this is moment of inertia of the particle mass times the perpendicular distance squared. Now the axis of rotation is perpendicular to the page of the paper. Okay, this is a perpendicular distance. All right, so we get the formula: kinetic energy equals half moment of inertia times angular speed squared. Okay, so the formula for rotational kinetic energy is simply half times moment of inertia times angular speed squared. Okay, now example. Suppose we have the following particles. Let's say I have the following coordinate system. It's 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3, negative 1, negative 2, negative 3. Okay? Alright. Suppose we have the following system of particles. So let's say we have this mass over here. Let's say it's m1 equals 1 kilogram. Maybe we have another particle over here. Let's say this is m2 equals 2 kilograms. And then let's say we have another particle over here, which is m3 equals 3 kilograms. Okay? Let's say these are connected by a massless sheet, a massless plate. Okay, and they're rotating about the y-axis like this. All right, so let's say they're rotating with angular speed of 2 radians per second. Okay, the question is calculate the rotational kinetic energy of the system of particles. Okay, so let's say the system of particles shown, the system of particles shown are rotating about the y-axis, with an angular speed of 2 radians per second. Okay, 2 radians per second. So the question is calculate the rotational kinetic energy. Calculate the rotational kinetic energy. All right, so we want to find the following. This is what we want to find, the rotational kinetic energy. But we know that this is a formula for the rotational kinetic energy, half I omega squared. Okay, so we're told omega is 2 radians per second, but first we have to calculate the moment of inertia of the system. Okay, now there's 3 particles, so the moment of inertia is m1 r perpendicular 1 squared plus m2 r perpendicular 2 squared, m3 r perpendicular 3 squared. Okay, now let's look at the perpendicular distances. This is m1, it's rotating about the y-axis, so this is our axis of rotation, and the perpendicular distance is simply the x-coordinate. This is the perpendicular distance, okay, which is 2 in this case. So we can say that let's say m1 is 1 kilogram, and our perpendicular one is simply x1. It's rotating with the y-axis. And then we have m2 equals 2 kilograms, okay? And the perpendicular distance for this one is this one, the x-coordinate, all right? That's also 2, okay? So we have, that is 2, and then our perpendicular 2 is absolute value of x2, that's also 2, okay? You see, particle 3 is on the axis of rotation itself, so it's 0. The y-coordinate for this one is 0. That's the perpendicular distance, okay? So for m3, which is 3 kilograms, we have r perpendicular 3 equals absolute value of x3 equals 0, okay? Now you see, if it was rotating about the x-axis, then the perpendicular distance would be the y-coordinate, okay? All right, so let's plug the numbers. So moment of inertia is m1, 1, times r perpendicular 1, 2 squared. m2, mass is 2. The perpendicular distance is 2 squared. And then we've got m3, and the perpendicular distance is squared. So the moment of inertia is 4 plus 8, 12. Okay, so this is 12 kilogram meter squared. Okay, now the kinetic energy rotational is half times I times angular speed squared. This is half times I, which is 12, and the angular speed is 2 squared. Okay, so that is 24 joules. Remember, the unit of energy is joule.